Hello everybody. Today I'll be evaluating the Gaussian integral, which is integral with boundaries from negative infinity to infinity, e to the power of negative x squared with respect to dx, okay? dx. So our first step here is utilizing the dummy variable. So I'm going to write, by the dummy variable, the integral is also equal to negative infinity, e to the power of negative y squared, is dy, okay? And we can use this because if you integrate with respect to a different variable, it does not matter what variable you choose. So if we're just denoting the variable we're using here, right? So if I can just simply swap x with y to z to a to b. So I'm just going to choose y here, okay? So now I have this equivalent integral form, okay? Then I can multiply both of these integrals. So then we can multiply both integrals. Which are equivalent to one another, so we can just rewrite as I squared to obtain I squared is equal to negative infinity e negative x squared dx multiplied by negative infinity to infinity e negative y squared dy, okay? And then what I can do here is I can combine every element here, like fourth, so I can combine the integral sign here, and I can also combine the integrand, what we are integrating, and I can combine the respective differential elements dx and dy, okay? So this becomes like such, infinity, e negative x squared plus y squared, because what I'm just doing here is using our exponential laws. So I multiply e to the power of negative x squared multiplied by e to the power of negative y squared gets this, okay? Simple algebra. It's dx dy, right? I'm combining the differential elements together now. I'm just pairing them up, okay? So what I have here now is I have I have a double integral in the Cartesian plane, okay? Now, if I want to evaluate this, I'm going to have to switch to polar coordinates, okay? Switching to polar coordinates, I simply let x equals r cos theta and y is equal to r sine theta, okay? Now, let's just visualize this using a graph, okay? So what I have here, basically what I'm trying to get to you is, let me just draw y, x coordinates, and let me draw a circle, okay? So I can denote this as y, x, and the circle here, this unit circle here with radius r. So this circle here, sorry, centered at the origin with radius r, denotes the polar form, okay? So I'm sure you guys are aware with this. I can denote this simply as the length r and the angle theta. Now I can just let x equals r cos theta because this is x and this is y. So if I want to map every x and y coordinate onto this circle or onto the polar coordinate, I have to let theta vary from 0 to 2 pi, right? So that the entire circle is mapped. And I can let r range from 0 all the way to infinity, right? So that I get another circle, okay? So I get another circle, so forth, which maps every other coordinate, okay? So that's basically the main idea we're using here, okay? So the new boundaries become this, right? So I'm going to write then integral squared is equal to theta is equal to 0 to 2 pi to map every coordinate, okay? R starts from 0 because it's a length, it has to start from 0, right? To infinity. And then I can write j, and I'll get to what j means real quick. E to the power of negative r squared times dr d theta. And we switch to dr d theta because we're integrating with respect to r and theta now, okay? Not x and y anymore. And the j here is basically what we call the Jacobian, okay? Which is a tool similar to u substituting when you're integrating with respect to one variable. So, you know, if you need to use the reverse chain rule in integration with one variable, usually use u substitution. In multivariable calculus, or when you integrate with respect to more than one variable. So we use the Jacobian to switch between polar coordinates and other coordinate systems, okay? So I'm just going to write that down. I'm going to write an important note. We use the Jacobian to switch between coordinates, okay? Between coordinate systems. It's analogous to U substitution when you're integrating with respect to one variable, okay? And what is the Jacobian? Okay, so the Jacobian basically is, the Jacobian is basically is the determinant of a 2x2 matrix. Okay, it's determinant of the partial derivatives formed by our substitution. So the first entry is dx over dr, and then I have nabla x over nabla theta, nabla y over nabla r, nabla y over nabla theta. And if you do not understand it, that's okay. You will learn this in multivariable calculus. But for now, just know that the Jacobian is the determinant of a matrix formed by partial derivatives, basically, okay? And this simply is just equal to, if you know the determinant formula, cross product here, cross product like that. It's basically nabla x, nabla r, multiplied by nabla y, nabla theta, minus del x over del theta, whatever you like to call it, or times by del y over del r, okay? So what is del x over del r? So we have x equals r cos theta. So if we are, so I'm going to write this here, x equals r cos theta, y is equal to r sine theta. So the partial derivative of x with respect to r is simply cos theta, because we're holding cos theta as a constant, right? So really we're treating cos theta as a constant, and we're differentiating with respect to r. So it becomes just cos theta, okay? So this becomes cos theta multiplied by what's dy over d theta, holding sine theta as a constant. Holding r as a constant since we're doing a partial derivative with respect to theta, sorry. So it would just be r cos theta, okay? Because r is a constant in this situation. Similarly, it would be differentiating cos theta to get negative sine theta, negative r sine theta since we're holding r as a constant, r sine theta multiplied by dy over sine theta, okay? Holding the sine theta as a constant, and then we're differentiating with respect to r here. Simplifying this further, we have r cos squared theta plus, because the two negative signs cancel each other out, r sine squared theta is simply equal to r using our trigonometric identities. That sine squared theta plus cos squared theta is equal to 1. So now we can just simply evaluate the integral here. So j is equal to r. So what we can just do is write I squared is equal to integral from theta to 2 pi. R is equal to 0 to infinity. R e negative r squared times dr d theta. Can we write this integral like theta is equal to 0, 2 pi. I'm going to have a big bracket here, and you'll see why soon. Can we write the integrand as I equals to 0, infinity, r e negative r squared, dr, bracket again, d theta, okay? Notice that this is equivalent. This is the same integral, okay? It's just we're putting a bracket, okay, around one of the integrands, around one of the integrals, okay? So now what I'm going to do is I'm going to use the reverse chain rule, because I know d over dr e negative r squared is equal to negative 2r e negative r squared. I'm going to utilize this fact. I'm going to pull out a negative half in front of our integral, double integral. I'm going to write this like this. R is equal to 0, infinity, negative 2r e negative r squared times d theta, which is just simply equal to negative half. Theta equals to 0 to 2 pi, bracket, e to the power negative r squared, right? Using the reverse chain rule, evaluated from r is equal to 0 to infinity times d theta, okay? Which is just simply negative half theta equals to 0, 2 pi. What is e to the power of negative infinity squared? That approaches, what does that approach? That approaches 0 because it is a decreasing function, okay? It would just be 0. And what is it at what 0? When r is equal to 0, it is e raised to the power of 0, which is just simply 1. It's d theta is equal to negative half theta equals to 0, 2 pi negative 1 d theta, which is now very simple to evaluate. It's equal to half, right? Changing the signs. Theta, 2 pi, 1 times d theta is just simply equal to half 2 theta minus 0. It's equal to pi, sorry, not theta. So therefore, this is I squared, not I, okay? Remember? I squared is equal to that. And because I is greater than 0, therefore, the integral is just simply equal to the square root of pi. Okay, so this is how we would evaluate it using polar coordinates, okay? So this is my full solution here. And yep, I hope you guys understand this. Okay, and I'll see you next video. Thank you.